In this video, we are going to be covering section 5.2 and 5.3 that covers power functions, polynomial functions, and polynomial function graphs. Let's start with our factoring warm-up. In this first one, we will go ahead and factor out the 3, and we're left with x plus 6. And the next one, we'll go ahead and factor out a 2x squared, leaving us x minus 4 inside those parentheses. And for that third one, I'll go ahead and factor by grouping. I'll take out x squared, and I'm left with x plus 3 inside, and I'll take out a negative 9, and I'm left with x plus 3. Rewriting this will yield this expression. I could leave it like that. You could continue to expand x squared minus 9, but that would be unnecessary. For this next one, we're interested in solving. So we're going to use u substitution because we have a power of 4. I'm going to say that u is equal to x squared. So that way I have u squared minus 5u plus 4 equals 0. So I want to multiply to 4 and add up to negative 5. So I'm going to say u minus 1 and u minus 5 is equal to 0. So now I have u equals 1 and u equals 5, keeping in mind that this is actually x squared equals 1 and x squared equals 5. So x is equal to plus minus 1 and x equals the square root of 5, keeping in mind it's a plus and a minus. Okay. Now, power functions are anything that have an exponent, any function with an exponent, okay, and the highest degree determines the power of the polynomial. Okay. And the coefficient is the number in front of the variables. Okay. So for example, if we had 3x to the 4th plus 2x cubed, yada, 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 okay, the coefficients are the 3 and the 2, okay, the highest degree is the 4, okay, and that determines the kind of power you have. Okay. There's two ways to write these polynomials. We could write them in standard form versus factored form. It's similar to quadratic. So a standard form might look like this. And standard form is going to be highest power to lowest power, whereas factored form is going to be sets of factors. For example, maybe x minus 1, x plus 2, x minus 4 squared. Okay, so you could write them in either way. One can be more convenient than the other. There are the even powers and the odd powers. So let me show you what those are going to look like. So we're used to seeing quadratics. So a quadratic will look something like this if it's positive, and it'll look something like this if it's negative. Pretty straightforward. If it is a power of 4, it tends to look like a W or an M, depending if it's positive or negative. And if it's a power of 6, if it's positive, it'll look something like this or something like this. Okay. Now, the reason we know it has that many curves is the power determines the maximum number of x-intercepts. So notice that the power of 4 can have up to 4 x-intercepts, whereas the power of 6 can have up to 6 intercepts. It can have less, so that is always an option, but it cannot have more, okay? Highest power determines determines maximum number of x-intercepts. It can also have as little as 0. 0 real x-intercepts. Okay, maybe our curve is fully above the line or fully below the line. That does happen. And for our end behavior, as x approaches negative infinity, this is for our positive one, y is going to approach infinity. And as x approaches infinity, f of x still approaches infinity. For our negative functions, we have as x approaches negative infinity, f of x approaches negative infinity, and as x approaches infinity, f of x still approaches negative infinity. So that's useful information to have for us. Moving on, we have the odd functions. Okay, the odd functions are going to look slightly different. So for a positive power of 3, it'll look like this. For a negative power of 3, it'll look like that. Power of 5 will have up to 5 x-intercepts, either starting low, going high, going high, or going high and then going low. So here's your 3 potential x-intercepts for the power of 3, and your 5 potential intercepts for the power of 5. Okay? Keeping in mind this is for positive and for negative. So, same thing as before, the power determines the maximum number of x-intercepts. However, these must have a minimum of 1. 1 real x-intercept. Okay? Because eventually, since they are moving in opposite directions, it does have to cross the x-axis eventually. So let's do our end behavior. End behavior for our positive functions. As x approaches negative infinity, f of x approaches negative infinity, and as x approaches infinity, f of x approaches infinity. For our negatives, as x approaches negative infinity, f of x approaches infinity, and as f of x approaches positive infinity, f of x approaches negative infinity. Okay? If we want to find an x-intercept of a polynomial and it's in factored form, it looks really similar to working with a quadratic. All we need to do is set each of these equal to 0 and solve. That would mean we have 2, -1, and 4. I'll go ahead and sketch that. So let's say 2, 4, -1. Okay. My y-intercept is going to be the numbers on their own multiplied together. So -2 times 1 times -4, which will be 8. Okay. So we'll write an 8 right there. And I know that this is a power of 3. There were 3 x variables. And I know it's also positive because there was no negative anywhere at the front. So I know that my end behavior is going to look something like this. So if I sketch, I know I start low, I go up, I will come down. Let me rewrite that. There we go. I'm going to go down and then come back up. Okay, that is my function when it's graphed. The next one is very similar. That's something to pay attention to on this one, though, is that this is also an x-intercept, which means it's at 0. And here are my other ones. So I have a point at -1, 0, -3, and 5. That means my y-intercept is also 0, 0, since I'm at the origin. I know that this is a power of 4, and it's negative because of the negative up front. So I know my end behavior looks something like that. So I start low, I go up and down and up and down again. So that's going to be the graph of the polynomial, or a sketch, I should say, for this function. Finally, let's practice this. So if I look at this first one, I know it is a power of 3. I know that it is negative. My intercepts are 2, 3, and -1. My y-intercept is going to be -1 times -2 times -3 times 1, which is -6. So that is enough information for me to graph. I know my end behavior is going to look like this. 2, 3, -1, -6. So I'm going to go down, and then up, and then down. On my next one, I have a power of 3. It's positive, intercepts at 0, -2, and -4, which means my y-intercept is also at 0. So my function is all the way over here, and behavior is going to look like this. Down, and then back up. My next one is a power of 4. It is positive, roots of -3, 2, 3, and 4. Okay. My y-intercept is going to be 3 times -2 times -3 times -4. Okay, so that'll be 6 times -12, or -72. So it's way down here. It's a power of 4, and it's positive, so I know it's going to be that W shape. So I'm going to go ahead and draw that curve. My last one on this page is also a power of 4, but it is negative, with intercepts at -5, 2, -1, and -2, with a y-intercept of -1 times 5 times -2 times 1 times 2. So that's going to be 10 times 2, or 20. So -1, -2, 2, and -5, with an intercept at 20. Since it's negative, it's more of an M shape. So I start low, go up, down, up again, and then finishing going downward. Okay. Finally, we have multiplicities. Okay, multiplicities are when there are exponents outside of the parentheses. In this first one, we have a multiplicity of 2. Okay, so we actually have a power of 3 because this can be rewritten as x plus 5 times x plus 5 times x minus 2. It is positive. My intercepts are -5 and 2. My y-intercept is -50, because 5 times 5 is 25, times -2 is -50, multiplicity of 2. It means for us to have a multiplicity of 2 that it's going to bounce off of the axis, similar to how a quadratic would move, right? So if I graphed this quadratic, this could be x plus 5 squared. So the polynomial is going to do the same thing, but as part of the rest of the function. Okay, So it's going to look like this. I know that I'm going to start low, touch, come back down, and then go up. Sorry, that was a little not quite straight. Okay. The next one is a power of 4. It's positive, intercepts of -1, 3, and 2. Y-intercept of 1 times -3 squared times -2, which will be -18, and a multiplicity of 2. So we're at -1, 2, 3, y-intercept of -18. I know it's that W shape again. So at positive 3, I know that I'm going to bounce just like that. Okay. All right, we also have multiplicities of 3. Multiplicities of 3. They're going to have a little bit different of a curvature. So this will be a power of 4. It's positive. It only has 2 intercepts. The y-intercept is 4 times 4 times 4 times -1, which is -64. A multiplicity of 3 means that it's going to look like a cubic function. 1, 2, 3, 4. So that might look something like this. So it kind of flattens out instead of going straight through. If I really exaggerate it, it'll look something like this, okay? So I know that at -4, we have that happening, okay? And so we're going to come down, really flatten, come back up to touch our x-intercept, and then come up. Okay? It really has a deliberate curvature to it instead of moving right through. Okay, let's practice this. This one is also a power of 4, but it is negative. It has intercepts of 1, -3, and 2. Oops, sorry, it's power of 5. Y-intercept of -1 times -1 cubed times 3 times -2. So that's -6. So 1, 2, -3, -6 over here. All right, so it's a power of 5 and it's negative, so we're going to start up here, come down. I have my multiplicity at 1. Oops. And then I'm going to come down at 2. Oops. Finally, we're going to write an equation from the graph. So I'm going to start with writing all my x-intercepts. I'm sorry, the screen keeps shifting around. So all my x-intercepts are here. So I have x plus 3, x minus 2 squared because it bounces, and x minus 5. Okay. I also have a y-intercept of -2. So I need to confirm that this function that I've written matches. So we have -2 equals a times 3 times -2 squared times -5. -2 equals 3 times 4 is 12 times 5 is -60a. And a is going to be 1 over 30. So that means the correct function is going to be 1 over 30 times x plus 3, x minus 2 squared, x minus 5. Okay. We find a because a might be a stretch factor that we otherwise wouldn't have found unless we plugged in the y-intercept to find another point, find that stretch. Let's practice these last two questions here. Go ahead and start by writing out what you know, which is my x-intercepts. Okay, I'm bouncing here, so that's squared. Okay, let me plug in my y-intercept and solve and see if that gets me the function I already wrote. So negative 60 equals a times negative 20 times 9. So that's negative 60 equals negative 180a. And if we divide, that's 6 over 18. And if we simplify further, that's 1 over 3. Okay, so that means my final function will be y equals 1/3 x plus 5, x plus 3 squared times x minus 4. I'm running a little bit out of room here, but I will try to fit this part in and move some stuff around. There we go. This last one, we have x plus 2, x plus 1, x minus 3. We can set it equal to negative 30 and solve. Negative 30 equals negative 6a, and a is equal to 5. So we have y equals 5 times x plus 2 times x plus 1 times x minus 3. That would be the function of that graph. Okay. That covers everything you need to know for polynomials so far.